Hello and welcome to my commentary on my presentation. It's I guess I'll take the time now to thank the organization, World Obesity and Weight Management Congress. I'd like to thank Dr. Russell Rising for just being so lovely and polite, even though I challenged kind of like his life's work. Not like it gets complicated, as you will see. But I do appreciate Dr. Rising and Andy and so many other people, Ben, who were there and just kind. I forget the lady's name, but she was so sweet. She called me, I might be the next Elon Musk, her words. I appreciate it. This is like, I want you to take this as like a presentation of evidence. This is how I see um, everything working out. And so uh, this is going to be more, I'm going to stop and comment on things that I think I did wrong and I could have done better, mostly. So let's get into it.
Thank you. I have a lot of information to go over and not a lot
And
of
I'm going to
time.
be
Last time
eating
I
while I
timed
do
this out, it
this.
was 25 minutes. So hopefully this goes a little bit better. Uh, here. If you want to contact me, feel free to. But we will keep going. This is in progress. It might change, not so much the key features, but some details may change as I get a better understanding of everything that's going on in the body. This project is also self-funded, meaning I work full-time at the same time, so I do this as much as I can. And it's just me. I'm the only one who's working on this project. Hope is to inspire now. Come back in 2 years to actually talk more, and then
So what would I expect to change? I don't know. That's kind of the idea. Is like there are known unknowns, and so this happened to me several times on this journey already, where I was told one thing about how to interpret data or how the world works, and I discovered another. So when I started discovering like element biology, which is like basically inorganic atomic biology, like how do the atoms interplay with biology? Um, and it's mostly like inorganic biochemistry, molecular nutrition, which is just like macroscopic um, nutrition, or like I guess it's microscopic, but it's macroscopic energy, and cellular biology, just like the processing of everything. Being self funded, most of my resources I find are just free online, or it's like what I spend my money on. I mean, what I spend my money on is food. I'm going to be honest. It's. I was also thinking of doing an counter for this thing because I say so much. But I guess it's turning into more of a commentary. Um, yeah, it's totally self funded. I just started a Patreon if anyone's interested. But it's more about just doing it right and getting it. I'll get there eventually, where this will be like self-funded, self-funding itself. Like the research will fund itself. It just takes time. It just takes time. But yeah, let's inspire
reporting in
now.
2030.
Get on to it.
Hopefully I'll finish my nutrition section and I can focus more on exercise. That'll make more sense as we continue. So we use, these are our current our current models in just measuring metabolism. I'm going to be investigating.
I had a slide at the very end that kind of talks about how we should go to different models. I don't think it was included in this video. Um, I'll try to find it in editing to put it up. But basically, everything that has the word metabolism we can keep, but everything that has this thermic effect is questionable. Like non exercise activity thermogenesis is literally just activities of daily living. Um, it's the idea that thermogenesis, oh, we'll
Calories
get right into it.
specifically, calories in, calories out, and trying to understand the validity of it, just try to get a deep understanding. What we understand now is thermogenesis and metabolic work are interchangeable, essentially. So the calories in, calories out, whatever you eat turns into this energy, this heat, and we can measure that in order to determine the total energy in the body. This was originally system we use today is from Olin Atwater, Wilbur Olin Atwater. The first time I read about his publication, other people have cited earlier writings from him, but the first one I've seen is 1894. The one that is referenced today is usually.
I wish I spent more time on this slide. The one I've seen before is referenced from a paper from a professor from the University of Georgia, who is the only other person I've really seen that go into the history of nutrition kind of this deeply. And he talks about 1887 being a year where the first year Atwater published his ideas about the calorie. He didn't really talk about Max Rubner though, but he did talk about 1887 in Atwater, and I just haven't seen it. I think I looked for it for a little while, but I just focused on these because they were good enough.
The 1902 model publication, as you can see here, it's referenced in the veterinary science book. This is the original, and this is our modified. It's a very slight change to our calculation on the 494 rule. There are alternatives.
The slides, just so you know, going from Google Slides to PowerPoint. If your titles are too long, they'll come over. It's a slightly smaller proportion size. That's why that derivatives is tucked in there.
Got a little messed up.
Pop up.
This has a lot of information on it. All I need you to focus on is this last part where we're still measuring it in kilocalories as well. So we're still using this heat measurement.
The less you think about it, the easier it is.
Relate back to our metabolism. From his quote, the amount of heat given off in the oxidation of material is called the heat of combustion, and it is taken as the measure of its latent or potential energy. The unit is commonly called the calorie.
Something I realized after this meeting and on my next meeting was that oxidation, as Atwater describes it here, is not the same way we describe oxidation in our present day. There are different chemical processes fundamentally. Today we refer to oxidation as the transfer of electrons, and here he's talking about the combination of the element oxygen, and we don't hold that same definition today, which is interesting. You know, another reason why using the calorie today and using the calorie then is not the same, or it's not valid. Anyways,
the USDA was adopted in 1897 with the Atwater-Rosa experiments, and it's what we still use today. This idea that respiration and combustion has been as old as Western philosophy. The farthest back I could trace it back was Heraclitus, where he said, everything in the world, even gods and men, are made of fire. This would go on to inspire Aristotle's model of metabolism and of thermoregulation. As you can see on the left, the food comes into what would be the body, it converts into blood, and that creates fire and combustion in the heart, and the lungs bring in air to cool it down. That's Aristotle. This would eventually continue into our origin of calories, which was not with Atwater. He got this from Max Rubner. Max Rubner was a German physiologist. He produced this 494 rule between 1883 and 1894. The reason for the 10-year marker is because his supervisor delayed his publication. He didn't agree with his results. But it is from obituaries, and all the evidence says that he's the one who originates that 494 rule. He is also the one who discovered the surface area law of heat, so that metabolism can be measured by the surface area is proportional to the surface area. And this is going to lead into
part of this commentary is like notes for me, and I think it'd be best to do, like, I like this approach, like go Atwater into Max Rubner, which is the direct link, and then Rubner talks about Lavoisier, Myers, and Helmholtz. Then I should talk about Lavoisier, and then maybe just walk history from Lavoisier to Liebig, into Faraday, into von Voigt, and then back to Rubner, and then back to Atwater, and then go into modern physics from there, the discrepancies, and then go into the difference between Emmy Noether and Dr. Lulu Hunt Peters. I don't really need to get into the argument against conservation of energy. I don't think I need to. I think it's just not necessary. The idea that heat and work are the same type of energy is probably an easier approach for a classical mechanic mindset. I just don't know enough about quantum mechanics and abstract algebra and systems of symmetry to really comment on Noether and if biology is asymmetric and we don't conserve energy in that way. It's very interesting to think about, I think. It'll be interesting to explore. But for the sake of now and current arguments, I think I should just kind of, I don't know. I feel like it's necessary to bring in for the conservation of energy. Maybe I should go modern physics into paradigm shifts. I don't know. Yeah, I don't know.
To the 494 rule that we use today. In context, in his
I do approve
experiments,
of
an animal
Lavoisier,
that
though.
is starved and freezing can maintain body temperature by roughly 4 kilocalories per gram of carbs and protein, or 9 kilocalories per gram of fat. And that is going to be the essential basis of the 494 rule. And it's not a very big sample
Isn't it
size as well.
crazy?
His experimental sample size, I don't
Look how small this sample size is to establish the 494 rule. Isn't that crazy?
think would be very well credited.
To personal note, I haven't finished reading that entire book. I got to read it and understand it. But if it's anything like Lavoisier, it'll take me a year. It'll take me like a week to read it, a month to start like piecing all the pieces together, and then a year to start understanding it.
Today. But this idea is that the law of the maintenance of energy, so the law of conservation of energy, which was a few years earlier from Helmholtz, which we'll get into, assures us that if we understand one form of energy, we can understand other forms of energy. So that way we can use heat measurements and chemical measurements interchangeably. And that's how we get to our indirect calorimetry today. As Rubner quotes, Lavoisier was the first scientist to take the physical aspect in addition of the chemical observations for the metabolism of animal bodies. He was very concerned about the heat of the body, how the body is able to maintain heat through the chemical changes. And as Lavoisier quotes and others, that the heat is a result of unique combustion of nutritional materials in the cells. Lavoisier thought this happened in the lungs. It'd be Liebig, 2 generations
Liebig.
above Rubner, who would say it goes into the blood.
I think it's
and diffuses
Lavoisier
and
too, not
combusts into the cells.
Lavoisier. Lavoisier.
These theories were only proven by Myron Helmholtz. He spells it with an E. I'm not sure why. That heat and work are essentially related, and we can understand one, we can understand the other. So we're going to slowly work into this. This is Mayer. He contributes
I
to
lost my presenter notes. I had the notes about like this information, and I was just gonna read it because it made sense when you read it. But trying to do recall and not recognition was so hard. I didn't have my presenter notes, and it was so. It makes me really like key in on the fact that bring flashcards, and just know what you're talking about before you're talking about it. So that way, if anything happens, that you could just keep talking about it. And I don't want to make that like a hard rule. It should be. It should be a more suggestive rule, but it's like, that's if I had that rule, I wouldn't be talking about this stuff right now. And so talking about stuff poorly is also a way to get to know where you're lacking. Sometimes you got to just put the metal test to the metal. You don't really know what you know and don't know until you're tested. And so I could have known more about this, and I wish I did. But I don't even know if all the pieces connect the way I wanted them to. But yeah, I'm trying to get, if I can get the keywords there, then maybe we can see the spiderweb design, and maybe my connections aren't the right ones.
Law of conservation of energy. Mainly, he's talking about how the energy of light is able to be converted into chemical energy.
I got to read his papers.
That was his first theory. He is trying to understand how this heat and work situation can work. How can you raise 1 pound of, how can you raise up weight, and at the same time, with that equivalent to a heat transfer unit, essentially. Sorry, I'm stumbling on the words, but this would be proven by James Prescott Joule with his mechanical equivalent to heat. Hermann von Helmholtz is also very prominent into the energy is conserved scene. He's also into electrochemical dynamics, chemical thermodynamics, and the mechanics of thermodynamics. He's also a big physiologist. He studied psychology and the physiology of vision. He got us out of the idea that visions are impressions into the eye and into sign theory, where they're translated into different stuff. He also has philosophies that we can't really know reality. He's a very interesting guy. And I got his information from Anson Robbenbach, who passed away earlier this year. His book, The Human Motor, is a fantastic book. He also attributes Rubner's thermodynamic energy as being valid.
If anyone wants to get into this kind of research, on like energy, I should have chewed first. If anyone wants to get into this research on like why exercise is important for society, then I recommend this book. It's a very interesting book on like social theory and the relationship of exercise science to social theory, like how society is formed, and it's really interesting. I think about it very deeply. This is really cool stuff.
But he introduced me to Helmholtz and all of his ideas. And essentially, Helmholtz's entire idea of conservation of energy is based on not watching machines, but watching the human body, and making the human body the model for how machines conserve energy, and not the other way around. Schrodinger also in more modern.
I really wish I kind of didn't put this in, or I put this in way later. When I was practicing this float in here, that's why it's here. I practiced this a couple times, and I would just like talk about it, go to the next slide. And when I would talk about something that was in a later slide, as you'll see, as I do several times here, I switched it. And so that didn't actually come out to work in practice. But I do think it's interesting, like, you know, Schrodinger's being tongue-in-cheek, like, this is absurd. And then the food content of menu cards is out of order. And I think that's just so unfortunate. But
times would talk about a little bit about menus. And the first paragraph, we don't have time to get into all this. The first paragraph, you can see that he calls the menus absurd, but to be fair, he called everything absurd. In this chapter, I think he's being a little tongue-in-cheek. And in the second paragraph in this note, he says that it's quite right that we measure the energy because we can't exchange carbon dioxide for oxygen. And I think it's these unfortunate conclusions by physicists that lead us into the day where we think thermodynamics is the right way, because obviously comparing these two, he hasn't really investigated if he's calling it absurd in his main body of text, and then a simple conversation, he's like, maybe it's useful. I think he's just leaving the door open rather than making a definitive conclusion. One of the biggest misconceptions in physics is the conservation of energy. It is not a universal constant. This was proven by Emmy Noether while she was working on trying to find solutions for Einstein's general relativity, because there were a few paradoxes. One of them was this idea of redshift in light. Where does the energy go from light if energy is conserved in the universe? And the simple answer is energy is not conserved in the universe. Energy is conserved in systems of symmetry. So when there's angular momentum conserved, it means that the physics are the same from the beginning to the end. For energy to be conserved, the physics of time needs to be the same in the beginning and the end. So the reason why energy is not conserved in the universe.
If you take a ball and you drop it from shoulder height, it will have a certain amount of energy. If you take the ball and raise it 5 feet higher, it'll have more energy. This suggests is like the physics acting on the ball are different at different heights, and that's because of acceleration. And so there isn't symmetry in that, and so there's like no linear symmetry or translational symmetry in falling balls. I remember that example. It's so strange. Like I said, it's above my pay grade. I need to
is because time changes
learn more about
physics.
it.
The light expands. The physics were supposedly different at the Big Bang, and they will be different at wherever we're going to end up. And so really, it just comes down to a question of, if we conserve energy, do we conserve time? But biology is noticeably asymmetric in time. We get older, we work out, and we get tired. And if both of those things happen at the same time, we get really tired and you start to feel the pain. And we've had this idea that respiration is combustion, even from Faraday, who talks about in his history of a candle, that it's more than an analogy. This is before we had the evidence to confirm that how oxygen and respiration in the body were. That would be.
I was going to pause it because I wanted to say, like, need to make a timeline.
Calorimetry and understanding metabolism. It is with Max von Pentenkoffer, but Voigt is credited with being the founder of modern nutrition, essentially. He is, like I said, perfected calorimetry, measuring all the gases. And one of the things he noticed is that if you breathe more, you're not going to get hotter. Your body's not going to get hot no matter how fast you breathe. You're going to just stay nice and cool. And this is different than technically the combustion method. Well, what I meant to say here was, as you work, the way to generate more oxygen would be to raise your metabolism. So it's not oxygen generation.
The way to increase oxygen demand or body heat is to raise metabolism through like working out and exercise. And that is different than just adding oxygen to fire. Like in normal combustion, you can add oxygen to it and it gets more hot. It's a very distinct chemical process of oxygen-based combustion. Like, because we'll get into nuclear combustion too. But when you add more of like the fuel, there's more heat. That's combustion, but that doesn't happen in the body.
Generates combustion, its metabolism generates oxygen demand, and this specifically is not exactly the same as a combustion fire, where if you do add more oxygen, you do add more fuel, you do get more hot. So this is the first time there's a scientific question into the validity that respiration and combustion are related. This is why his paper, Max Rubner, would be delayed by 10 years, because he did not agree with this result. Voigt himself thought the muscles were moved by protein turnover, and he was able to disprove that with his experiments of urine, nitrogen in urine. He was the first to do that. Wilbur Atwater would learn German to travel and study with Voigt, and during this time, he would also pick up the 494 rule from Max Rubner, bring it back to America, write his 1902 publication, and get associated with the system today. This would get spread around the world before it would come back to America in 1902. As you can see, it was also used in World War I to ration troops for both sides across the West. Someone who made it popular in America was Dr. Lulu Hunt Peters, a pioneer in women's medicine. The first female intern at Los Angeles General Hospital. She would also head the infectious disease unit, I believe. She would write this book, Diet and Health with the Keys to Calorie,
I wish I kept that slide up.
It would go. She would then leave for the
Try to go
Balkans on a
into
Red
date
Cross
order.
mission when several
So it was
awards come back.
1911.
Her
I was
book is a
talking about
bestseller.
1918.
She would go on a national speaking tour,
Actually, I just left that
and in
up.
this way, it became very popular. Radio's just coming around. She might be the world's first ever health influencer, talking about calories just by happenstance. Her book is very enjoyable to read. I highly recommend it. As you can see from her book, the picture is actually drawn from her nephew that she includes in.
The missing end quotes is actually not an error. I was doing that to show that it was leading into the next slide quote, and I think that it did not come off the way I intended. So it was an error in judgment, not an error in editing, to leave that quote off.
The general fattening value is the caloric value and the fattening value. And for her, she says, depends on the amount of fat and degree of concentration. But a reminder at this point, any food eaten beyond what is your system requires for energy is growth, repair, and fattening is fattening an irritant or both. Sorry, I'll try to slow down, but I know I got a lot to cover. And she cites the Atwater 1902, the 142 is the 1902 publication. The amount of heat given off in oxidation is the unit commonly called the calorie. That is what she is citing. That gets us back to where we are today. Essentially, that's the full loop. Let's investigate this kind of on an evidence claim.
Yeah, I wish
Even
this was
today, we
way in
referenced
front.
that
That's why I
Lavoisier
think that's like why this bill's disorganized. It should have been Atwater. Well, yeah, Atwater, Rubner, Atwater, Heraclides, and Aristotle. Lavoisier, Liebig, Voigt, Rubner. I did like the shock value though of Rubner. Maybe I should go Heraclides, Lavoisier, Rubner, and then fill in the gaps between Lavoisier to Rubner.
First to demonstrate the cellular site of respiration and combustion was whole animals, even though Lavoisier died in 1794 and the mitochondria wouldn't be discovered until about 1850, 1840. So this reference by a credible source like the Britannica is frustrating. This would be the world's first calorimeter. It's just called
mitochondria, 1857, I believe. Bioblasts. Yeah, Lavoisier thought that the heat combusted in the lungs, and then the energy was imbued within the atom, and then the atom was able to carry that energy into the body through the blood. That was his idea of like heat, that it was stored internally within the atom. People like Crawford thought that the heat was radiated off of the atom. And I think the right answer is a mixture of both. If I'm not mistaken, like the energy is definitely consistent with how Lavoisier said, where it's kept within the atom, and that's how we understand it in modern physics. Just fun fact. But he thought the combustion happened in the lungs.
Machine, because the word the calorie was not invented yet. The idea was ice melting instead of just water transfer. So as Lavoisier can measure it, ice, as heat is applied to the ice, the water will melt.
And I guess I could talk about the three chambers. So the open model, the calorimeter, you can see there's three chambers in there. The most outside chamber is for ice, for an insulator. The middle chamber is the ice melt that they're measuring. It was like crushed and slightly melted ice. And then the cage is where you had the experiment. There's little tubes you could see if you look closely coming out of the sides, and that was to supply oxygen to the experiment. And they did this experiment, they dry ran it to make sure like what the basis would be and if oxygen would flow in there naturally, and that's why the tubes are bent down to prevent like flow. Those tubes are actually connected to other apparatuses. Or is it just the handles cut in half? I'm just realizing that now. It might just be the handles cut in half. I don't know. Have to look into it more. They did have a tube to refer because they needed to supply oxygen to the site, and so I know he mentioned that. I just didn't realize. Yeah, I think those are handles for the entire apparatus because they go through it into the chamber, and the chamber is disconnected. The cage, I think. It looks like it sets in there with hooks. I think those are hooks and not the breathing mechanism.
The water
I thought
on
it
that
was.
surface level will maintain just roughly above freezing temperature. As more heat is added, that water doesn't change temperature, but more water melts. This implies the heat is transferred directly through the water and into the ice to be captured. So the problem with thermometers is they capture an average, and it takes a while for them to grow. But if you were to take an experiment and put it all in ice, the outside air would not affect the inside, and the inside on the reverse would not affect the outside. So the chemical reaction, you can measure the heat transfer.
I explained it much better in my
ACS
talk.
These experiments would be done with Pierre-Simon de Laplace. I know we use the capital L for the Laplace, but this is actually how you spell his name. It is de Laplace. And this is his conclusion we still cite from 1783. Respiration is combustion because of the similar compounds. This is also when chemistry was just being invented. This is when we're just discovering the non-vital air is carbon dioxide and the vital air is oxygen. The calorie would not still be defined for another 6 years. That would be in the world's first.
Maybe I should go Atwater, Heraclides, Aristotle, Rubner, Lavoisier, and then connect Lavoisier.
Chemistry textbook, Elements of Chemistry. The one on the left is this French version. The middle one is the first English translation. The one on the right is my copy edit. You can get for free. And so you can read the first chemistry textbook if you want, where he first defines the calorie, the first chapter. It's amazing. The calorie was gathered from an estimated 23 years of research. And the idea is it's this measure of repulsive force, whatever it can be measured at abstract. In Lavoisier in physics, there is three fundamental forces. There's the, at least for matter, there's the attractive force that brings matter together. There's the repulsive force that pulls it apart with heat. And then we need this atmospheric pressure. Otherwise, there would be no difference between the attractive force and the repulsive force. It would go from...
There would be a difference between the attractive force and the repulsive force, but it would be all or nothing, as Lavoisier says. Like either things would be impossibly bound together, and then the moment that they would reach that threshold of heat, that they would explode apart, never to return. But the atmospheric pressure allows for like liquids and things to like maintain their bodies.
Either being all together or completely spread apart. So we need this atmospheric pressure in order to allow experiments to continue. He did not, in the book where he defined calories, comment at all about body heat.
So yeah, while in 1783, him and de Laplace concluded, and really I think calorimetry is more of a Laplacian theory. The more I read about it, the more I keep referencing it. It's like the idea of water melting and ice melting. I'm starting to think that it was a de Laplace theory, that the origin of the model of calories is a de Laplace theory, not a Lavoisier theory, even though Lavoisier was the first to name it, just like oxygen. And so Lavoisier, the title giver. But here it's interesting, right? Like, so they already concluded that respiration was a combustion, but here they were really trying hard to make sure that anything that was inconclusive they didn't include, and so they didn't include that into this one where they defined the calorie. Not like how we used it today, and that's kind of like my point. It's like they had a theory on how this heat transfer or respiration is combustion in the body because of their experimental results, and then this, I think, suggests they had some questions about that results. And I really wish I could be a fly on the wall and figure out what questions they had in order to not include it here. Like, I can guess, but I would like to know what they thought.
Did not comment about his
I wonder if it's
original
written down
respiration as
anywhere.
combustion. He wanted this to be a very sterilized book on chemistry. He would unfortunately die 5 years.
I guess I'll do a commentary on my other video too, but this is what I mean when I say he is exonerated from calories and nutrition. Yeah, it seems like De Laplace, when they were reading out that conclusion on section 4, it was De Laplace reading it, but Lavoisier's name is on it. I'm just trying to, I'm very biased for helping my guy.
Publication during the French Revolution, because
maybe I should be more biased for helping out De Laplace.
He invested in the tax collecting system that was outsourced from the government. They did eventually, a year later, apologize. But so from Aristotle to Atwater, we've always thought respiration is a type of combustion. It is both ancient and modern.
And so I can get into this, like the timeline, respiration is combustion, Atwater, and then skip, like have that gap of how it got to us, and throw in like Lulu Hunt Peters, Ansel, Schrodinger. Like, this is the time when I should start throwing in those people who got us from Atwater to today on calories. I think that would be better. And then go into like modern, what it was missed with modern physics. What's the actual definition of combustion?
We still cite this
and
today,
oxygenation,
whether it's from Britannica
how that changed with modern physics.
And I want to get into this question of what is combustion. So we talk about, even Merriam-Webster has defined slow combustion as something else in the body. So I know combustion to be fast and rapid. What else in the world is this slow combustion? So I Googled, and I try to find out. And the other things were rusting was basically the only other thing I could find that was slow oxidation. So is rusting slow oxidation? India's biggest education technology company says, yes, it is. So is digestion. This is a form of combustion. Other people say no, like AI and other people online have said no. So I'm just trying to understand what even is combustion at this point. So I go to Florida State. They have their technical definition as well.
I don't go to Florida State, the college. I went to Florida State. I Googled what is combustion in Florida State, Jacksonville. I went to their website and they had this equation. I went to their website. I go to their website. Like, I don't go to the school.
Study.com, that is these hydrocarbons reacting with oxygen to create carbon dioxide and water. But there's a problem with this because there's hydrogen combustion, there's phosphorus combustion, and those aren't with a carbon source to begin with, and they don't produce a carbon source at the end. Even Lavoisier knows this in his book at the beginning. So does rust produce CO2? Not by our chemical equations. So this formula from our state college is incorrect. And we'll change this idea of carbon and oxygen being needed as we get into the modern age and with modern physics.
This is something that is kind of making me mad too. We got so, like, the information and the teaching pedagogy that we have out here today is completely like intertwined with what we need and what we don't need, because everywhere online that I could see, and I thought for the longest time that combustion needed oxygen until like I was doing this research, and then I thought aluminum and fluoride could combust together, but there was an oxide. It was aluminum oxide and fluoride. But this, I think, is the most clear example of a combustion process that requires no oxygen. It's based on neutrinos. It's crazy, but this would be a type of combustion by the next definition.
This is a nuclear combustion, and as the nuclear bomb combusts inside the bomb before it ever touches the oxygen, it is this chain reaction explosion where each intermediary process creates the next process. And that's because that is what a combustion actually is. It's a chain reaction process, not just any oxidative process. It necessarily needs this avalanche feedback. So that way it can have this combustion in this heat. And that is going to, well, I'll talk about Lavoisier on that in a second, but this is actually a problem in chemistry in general. This study from the University of Washington.
I don't say this next part very well at all.
So from different levels, grouped by their level, did not understand that combustion could happen without oxygen or carbon dioxide, or they would always put that at the end of their formula, that they produce carbon dioxide or it always needed oxygen. So this is an actual example of carbon combustion, where the intermediaries continue the reaction forward. And the definition by Lavoisier is not every oxygenation implies direct combustion. It needs that heat and that light to be disengaged. This is also just further on the chain reaction case, something that we still use today. There's different types of energy transfer without combustion. Just to be clear, there's kinetic, a gradient on a battery, and radiation. That battery one is going to be most important for us. There, again, because we can have hydrogen cells where we have the exact same equation for hydrogen combustion, but this is, I don't think anyone would call this a hydrogen combustion fuel cell. They're different thermodynamics. And so we can review again the cellular respiration. We know the equation up top is correct. Food and oxygen go in, energy, CO2, and water come out. So let's check it out. The food goes in, it becomes this acetyl.
I shouldn't have focused on acetyl since I just brought up the respiration. I should have just gotten into the respiration and then focused on acetyl.
And this acetyl group is going to be the main focus of everything we move forward for here, at least for me. It attaches to this coenzyme, and then that gets reintroduced into the citric acid. So all of these macronutrients can turn into this.
I edited my ums out on this video.
Key for weight loss and weight gain. This is essentially the transition. It is used in fatty acids, hormones. It's used across multiple things, but the most important thing is that it comes from these nutrients, carbs, fats, and proteins, not any other nutrient, and it can be stored as body fat. This is what we would consider the traditionally caloric nutrient. If we had to put it into a chemical form, it would be acetyl. Krebs cycle is anaerobic. It produces the CO2, but it is not from an oxygen transformation. It is from the acetyl from our food and from water that we drink. So the oxygen we breathe is never transformed into CO2. The oxygen we breathe is transformed into water in the electron transport chain, which is disconnected from the carbon that we use. It uses a hydrogen after the NAD and FAD are reduced.
The oxygen's brought in at the bottom with the plus hydrogen and half oxygen. Each half of an oxygen makes one water
in order
molecule.
to move through. Those are my seconds? Okay. And so you cannot combust carbon with oxygen if they never come in contact with each other. But essentially the sliding filament is the same thing. I was trying to ask tropomyosin dynamics.
So yeah, because the energy is combusted when the ATP inorganic phosphate is decomposed or separated by the ATPase, but it waits for the calcium control. Like it's already ADP in inorganic phosphate, but it still waits for the calcium control. So the energy has been combusted, quote unquote, but then it waits. That's not how a car engine works. The piston doesn't wait for the car engine to get into place before it releases the energy from a combustion. It combusts, and if it's there or not, it still releases that energy.
How does calcium move the tropomyosin if calories are the energy to move things? How else does tropomyosin move? It's from the electromagnetic pressures. The energy from biology comes from atomic structure, basically. The same energy that gives proteins the ability to fold and create conformational changes is the same energy we need to move. And our body just mediates those chemicals in order to create that movement. I don't really have time for anything else. I was going to talk about oxidation, modern physics.
So maybe in my next presentation, let me go back a little bit. I'll talk about this. I'll just get into this. Start with this and then lead into nutrition from there, and then talk about why calories don't meet this requirement, and then talk about the history of calories.
I don't really have time for anything else. I was going to talk about oxidation, modern physics. It basically, the idea is, Rubner's idea is that we can't understand the material energy, and modern physics says different. All of our calories are before modern physics. We had it in the USDA guideline the same year we discovered the electron, before we had a model of the atom. It's hopefully a paradigm shift. Going through the physics, everything we need to understand the electron transport chain, to understand everything we need to actually understand
this
the
myosin. This is actually like how a myosin head moves.
Or the myosin action in progress. So these are my deductions. I suppose I could start here.
I think these are deductions.
They're classical thermodynamics. Classical thermodynamics can't explain atoms.
Technically deductions.
And energy in that is from atomic structures. Thermodynamics is from acetyl. Two different thermodynamic pathways, whether it's coupled or uncoupled, for heat or for exercise. And the missing theory, especially note they're changing assumptions. Energy is not conserved, but mass is. Metabolic thermogenesis and metabolic work aren't
So the idea behind energy is not conserved,
changing
the
assumptions.
mass is. We
Energy
don't
is not
need
conserved,
to worry about this energy profile of food. We need to worry about what we're getting from the food, like how it's constructed, the reactants, and then the products. Like that's what we need to study for nutrition. What are we putting into our body?
mass is.
These are things we already know.
Thermogenesis and
This, I think, is a
metabolic
big
work aren't
point.
exchangeable. Thermogenesis is an element, but material exchange is equivalent for metabolic work. What's happening is electromagnetic conformations from the
I love
energy
this slide.
atom.
And
When
this
they
whole
bind,
section.
they create shifts. Those shifts create larger changes into the cell. Those larger changes in the cell create movement for you. This creates heat. Different temperatures create different conditions for chemistry. We need to maintain a certain amount of temperature for our chemistry to work, for that material exchange to function properly in the right kind of chemistry. That is, oh.
And then it's done. But yeah, I think that's about it. Hope you enjoyed this little video, and that's my commentary on my presentation. I'll do my other ones, after this.